Cool. Hey, what's wrong with this thing? Yeah, there's a bigger problem than that. Something should scream at you. Where's the O's? That's fun, right? And many of us were seeing this yesterday when we were kind of working on separating them into our half reactions. The problem is that the O's just kind of disappear into the ether. And that's not how law of conservation of mass works. What's law of conservation of mass say? You cannot create or destroy matter. We know you kind of can with like nuclear fission, but in normal chemistry, normal rules, you can't just have oxygens disappear as you're actually balancing your chemical reactions, which means we got to do a little extra work. And I want to start with the steps, give you some examples, let you try some. Not what's nice, we've done some good work kind of getting our half reactions in place, but we do kind of have to talk about the O's. Now, there's good news. There's an imaginary particle we get to use. Check your state symbols. What are most of your state symbols? Aqueous, which means what do we have available? Water. Does water have O's? Yeah, and that's how we're going to take care of our O's with some of the water. Cool. Let me take you through the official steps for balancing redox reaction. Step 1, we did it yesterday. Identify your oxidation numbers. Hopefully we're good at this. Hopefully we're feeling okay after the practice that we've had. Good news, we're going to get more practice. Yay. Everyone's so excited, I can tell. How dare you teach us new stuff in AP? Start by figuring out your oxidation numbers. Just like we're doing, we got all those rules we've been practicing. Cool. And then we're going to split them in half and balance our half reactions. What's nice is if we follow our steps, we're going to know early if something is going astray, because we have multiple checks actually kind of built in here to make sure that we're getting our half reactions and getting our reaction balanced. The other nice thing is it's going to help us build them coming back tomorrow. We're going to build a battery tomorrow. It's going to be fun. Cool. If you need it, oftentimes we know our batteries are filled with acid. This is a thing. Sometimes it's a base. Most of the time it's an acid. And so if you have an acidic solution, that means you've got free H+ ions floating around to help with this redox reaction. And we also have waters if you need some oxygens. You got some waters, you got some H's. And I'm going to get you some pro tips for this. This is going to feel a little funny because it's like, oh, we just had stuff. Yeah, we do, because it turns out there's more stuff floating around in the beaker than just the particles that we put in for our reaction. Cool. Then you got to get your electrons to match. We saw this yesterday where we multiply our two halves to get us that the number of electrons lost by the oxidation reaction match the number of electrons gained by the redox reaction. Then what? What did we do yesterday at this stage? Yeah, we put them back together. Yeah, you combine them and you get to cancel out your electrons. So you recombine your halves. And then you kind of look for spectators. There's going to feel a little bit like dead ionic here where we can start to knock out some of our spectator ions. The electrons are going to cancel out. Oftentimes the waters simplify out. The hydrogens will simplify out. If it's basic, I think the book gives you different rules. I don't want different rules. I just want to add a step if it is basic. And we'll see an example of this. If it is basic and you have extra H pluses, you got to get rid of those. You're not allowed to use those because you weren't in the acidic solution. We can pretend that we were and then swap it out for hydroxides at this stage. Oftentimes it's going to be acidic, so it's good to practice this, but we're not going to see this as often as we are the acidic solutions. If it's basic, you don't get to keep any of the H pluses. You got to swap them out for hydroxides, and then you'll do some extra canceling because you're going to end up making some water. Don't worry, it'll make sense. But the nice thing, just like in Chem 1, if you're balancing reactions, you can always double check it. And you're actually going to be able to check it at the half reaction step and at the final step. So you're going to have multiple opportunities here to check, is this making sense? Are we actually getting this to work that we want it, the way we want it to work? What do you think? Clear as mud. All right. For my folks watching video, if you cannot read what I'm about to write on the board, feel free to head on over to the PowerPoint. If you put it in presentation mode, it'll click through and actually have all these steps for you already pre-typed. For folks here, let's try one. Let's try one. Like, comment, and subscribe. Okay. Let's go back to that one we were looking at then. Let's start with our oxidation numbers. We know the deal. Let's do it. Okay. What's up? Love it.
Step 6 for the CR.
So chromium, we got 14 negatives total. We want 2 negatives left over. So we need 12 positives. There's 2 chromiums. So each one would be a 6+. Cool. If it's ions, it's just whatever their charge is. For our element, it's going to be 0. We can kind of partner them up then. We've got 6+ going to 3+. Our charge is reducing. We are gaining electrons here. To go from 1- to 0, we lose some electrons. Which one's oxidizing? Your I is oxidizing, and your chromium, which is unfortunately tied up in this polyatomic, is gaining some electrons, getting reduced. Just identifying my 2 halves. Couple of ways we can slice this onion. Couple ways we can slice this onion. We got I- going to what? I to I- to 0 means that it's losing 1 electron. The problem is how many iodines we got? 2, which means each iodine is losing electron. We're losing a total of 2 electrons. Another way you could check that, right? Because if you know it's I going to I2, you're going to have 2 of them. That makes 2 negative charges. 2 negative charges to balance. A couple of different ways, again, that we can kind of creep up on our numbers here. Okay. Yeah, this one. This is turning into Cr3+. How many chromiums? 2. So we're going to need a 2 here. Another problem. We got O's. And we got an acidic solution, which means what else is floating around in our beaker? Whole bunch of hydrogen, H+, and H+ and O's will make water. And so we're going to get rid of these O's using water. How many waters am I going to need to balance these O's? 7 O's, which means I'm going to make 7 waters. But wait, I hear you cry. Where did the hydrogens come from? They came from the acid. We got a strong acid floating around that we know wants to donate H+. Pro tip, your H+ are always going to go on the side with the electrons. Because we got another way we can kind of double check this, right? Our chromium is gaining to go from a 6+ to 3+. We got to gain how many electrons? 3 for each chromium, right? Chromium's going from a 6+ charge to a 3+ charge, but I got 2 chromiums for a total of 6 electrons that I need. All right. So how many H's do we need?
14.
14? We're going to snag 14 hydrogens floating around in the water on the same side as our electrons. And here's, sorry, time out. We can check it, right? What's our, we got 14 H's, 2 CRs, 2 CRs, 7 O's, 7 O's, and then we can check our charge. How many negatives? 6, 7, 8. We got 8 negatives and 14 positives for a total of 6+. What we got going on the product side? To get rid of my O's. Yep. Cool. What's our next step? We got two balanced half reactions. Well, before we combine them, we need to have, we got to multiply to get the electrons the same, because over here we're gaining 6 electrons, but we only lost 2. Multiplied by 3, this turns into 6i minus, going to 3i2s plus 6 electrons. Oh boy, we're having fun now. Now we can combine them because we're losing 6 electrons. We're gaining 6 electrons. If it helps you kind of keep your arrows in the same spot, because we're adding 6i minus, I'm just bringing this reaction over. 6i minus is turned into 3i2s plus 6 electrons. We got 6 electrons on the left side, 6 on the right. Anything else? Anything else cancel? Okay. Put them together. 14H plus floating around in solution. It's combining with our Cr2O7, also in solution. And our 6i minus, also in solution, to form 2 of our chromium ions. 7 waters. State symbol on water. Liquid, thank you, plus 3i2s. I think we get to be done because we were already in an acidic solution. Don't have to worry about those H pluses. Should be able to double check, yeah? Does it work? 14 hydrogens, 14 hydrogens, 2 chromiums, 2 chromiums, 7 oxygens, 7 oxygens. 6 iodine, 6 iodine. Net charge of 6 plus and final answer. Would you have been able to go from this to this? No, without the steps. Follow your steps. I'll get you there. There's an acidic one. Probably see a basic one, yeah. Good news, the first steps are the same. Almost done. Hang in there. Yeah, so if you're on the PowerPoint, hey, we got it. Good. Illuminati confirmed. Oh, I'm going to get banned for that. Cool, Tristan. First step. Oxidation numbers. Great. 8 negatives, 1 left over. Ooh, okay. Love it. 8 negative, 2 left over. 6 negatives, 6 positives. Each one is 3 plus. 2 minus in the oxygen. That's 4 negatives total. 4 plus on the manganese. 2 minus on the oxygen. 4. What's happening to our manganese? Gaining electrons. That's our reduction. Getting reduced from a 7 plus down to a 4 plus. Going from 3 plus to 4 plus. That means we're losing electrons. We're getting oxidized. We found our 2 half reactions. Let's split them up. We got C2O4 2 minus. Change it into CO3 2 minus. Just get my pieces here. Ooh, but we're also losing some electrons, right? You know, there's just gonna be some electrons popping off for oxidation. So oxidation, your electrons are always gonna be a product. For reduction, your electrons are gonna be reactant. Kind of helps keep it in place for us. So on our reduction side, we got MnO4, 1 minus, gaining some electrons. We'll figure out how many here in just a second. Turn into MnO2. How many carbons? We got 2 carbons here, 1 carbon here multiplied by 2 to get the carbons. All right, I'm just getting my carbons the same. Each carbon is doing what? Or do you want to work it the other way? You want to work it back the other way? Let's do it the other way. Ooh, let's do it the other way. Because how many O's? 4 O's. How many O's? 6 O's. We need how many more O's? 2 more O's. So 2 more waters over here. Can I do that? So if I start changing these numbers, it's going to keep changing forever. How many H's? 4. So we need 4 H pluses on this side. Should be on the same side as your E minus. Ooh, now check our charges. Got a 2 minus here. All right, 2 minus on the left. We got 4 minus, 4 plus. They're canceling, but I need to have how many left over? I need 2 minus. How many electrons? 2 electrons. How many carbons? 2, and each one is losing 1 electron. So I just work backwards to the electrons. Works either way. Works either way. Cool. That sounds good. What we got over here? 1 manganese, 1 manganese, 4 oxygen, 2 oxygen, add. We need 2 more O's, right? 2 waters. Oh, how many H's? We're gonna need 4 hydrogens on this side to balance the H's. Ooh, 0 charge over here. That's fun. I got a negative. Sorry, that's a negative on my electron. I got 4 positives. 1 negative. I need how many more negatives? 3. 1 manganese went from 7 plus to 4 plus. Gain 3 electrons. It works either way. Whatever makes sense to you. What's the lowest common multiple between 2 and 3 electrons?
6.
Oh my! Multiply this by 3. Multiply this one by 2. Here we go. We got 6 waters plus 3 C2O4 2 minuses going to 6 CO3 2 minus plus 6 electrons plus 3 times 4 is 12 H pluses. All right, that was fast. So on this side, we end up with 2 MnO4s plus 6 E minus plus 8 H plus, 2 MnO2s plus 4 H2Os. Which one's going to be easier to rewrite? They're about the same, aren't they? I'm gonna leave this one. I'm gonna just pull over my reduction so I can add them together. I got 2 MnO4s plus 6 E minus plus 8 H plus going to 2 MnO2s plus 4 H2Os. Ooh, we have to get rid of a bunch of stuff. It's gonna be so pleasing. What's the first thing we should get rid of? Electrons, 11. Whoosh, whoosh. What else? You can get rid of 4 H2Os. Yeah, absolutely. We got 4 here. We got 6 over here. So this changes to, is it easier to do it this way? Changes to 2 waters on this side. What else? Hydrogen. Yeah, we got 8 hydrogen here, 12 up here. So this drops down to 4. Now I think we've canceled everything again. I'm gonna come over here, just rewrite it then. We got 2 H2Os plus 3 C2O4 2 minus plus 2 MN, sorry, block that off. 2 MnO4 1 minus. Reactants. 6 CO3 2 minuses plus 4 H pluses plus 2 MnO2s. Close. If this is acidic, we'd be done. Well, we're not. What are we? We're basic, which means we can't keep this. It's okay, easy fix. Instead of H pluses, we got to use OH minuses. How many H pluses are there? 4. So we're just going to add enough OH minuses to get rid of those. If I'm going to add them to one side, I got to keep balanced. Right? I'm balanced at this point. If I add 4 to this side, I also have to add 4 to the other side. I got to keep it balanced. Oh, okay. What does this turn into? That turns into 4 waters, yeah? So now I end up with 2 H2Os, 3 C2O4s, plus 2 MnO4, 1 minuses, plus 4 OH minus on the reactant side. It's this whole side. Over here we get 6 carbonates plus 4 waters. So plus 2 MnO2s. What's the last thing we check? Reconcile our water. We had 2 waters over here, 4 over here, so we can get rid of this and put this as a 2. Oh boy. And here is the double-edged sword of balancing. You can always check it. 6 carbons. 6 carbons. Let's leave the oxygens for a second. 2 manganese. 2 manganese. We got, looks like 4 hydrogen. 4 hydrogen. How many total of those? We got 12 oxygen here, 8 here, 4 here for a total of 24 oxygen. 18 plus 2 plus 4, 24 oxygen. Oxygen's good. What's the last thing we use to check? Charges. We got 6 negative, 2 negative, 4 negative, negative 12. Hey, negative 12. Hey, we got it. Last thing, because it's going to matter when we get to our final, what do we got? 1 solid. When we get to building these state symbols, liquid, and everybody else is aqueous. All right, cop effect. It's easy when the teacher's there doing it with you. Got to be able to do it for yourself. There's a lot on that handout. Should we pick a couple? Should we pick 1 acidic and 1 basic? Sound fair? So on official homework on HO 21.2, pick me 1 acidic reaction you want to do, 1 basic reaction you want to do. I want you to try 1 of each for tomorrow. Sorry, Edric, what you got?
So we know it was acidic because of the H's.
I gotta tell you.
Oh, yes, sorry.
Yeah. So yeah, I was kind of covering up with the video. Yeah, I gotta tell you whether it's acidic or basic. If it doesn't tell you, assume acidic. Yeah.
So acidic, so.
Assume easier unless told otherwise.
So basic is when you have to.
Add those OHs in. Yeah. 1 acidic, 1 basic.